So today I'll be reviewing the paper by Tulcyzjew and Urbanski on Legendre Transformation for Singular Lagrangians. Right. So in mechanics, we have two broad ways to extract equations of motions or dynamics. One is the Lagrangian formalism, and the second is the Hamiltonian formalism. Right. In terms of the Lagrangian formalism, what happens is you have the principle of least action, and then there is the Lagrangian function that has to be kind of minimized in order to get the shortest path between 2 points, and that gives you the dynamics. However, what happens under this case is most often you don't have a real physical interpretation of what the principle of least action, or what the minimum path is in terms of quantum mechanics, right? Minimum path minimization is something that works extremely well in classical mechanics, but when it goes to the quantum, you don't have a real physical interpretation, and though people have tried to give path integral formalism, etc., right? It's the understanding of it, especially with the issue of time and how you treat time and all that, become pretty confusing, right? So often there is a need to shift to the Hamiltonian formalism, which actually doesn't depend on the any of these minimization principles or whatever, right? What it does depend upon, however, is like you have Poisson, or you have brackets, and you have a certain algebra, and then you have some sort of constraints that limit the dynamics of a system, right? So this is the Hamiltonian theory is in fact because it allows for the phase space and among other things, the Hamiltonian theory is more preferred, and it is somewhat easier to understand compared to the Lagrangian, especially when dealing with quantum gravity, etc. Right? So, well, in this talk, there are four key things that I want to talk about. One is the general structure of dynamics and how you get differential equations or dynamics from how you basically get them, right? Second thing I want to talk about is a little bit of about Morse families, and the Lagrangian and the Hamiltonian Morse families, and then how there is some sort of an equality between both of them, which leads to there being a need for a Legendre transform that takes the Lagrangian to the Hamiltonian. The third thing that I want to talk about is this is going to be a brief thing, right? How do you derive constraints, and what are exactly constraints, and how do they matter, right? And the fourth final thing, we will look at an example as to fourth thing, okay, so there are five things now. The fourth thing is we will look at an example as to how different Lagrangians lead to the same Hamiltonian, and then the fifth example will be an extensively worked out example that comes at the end of this paper, and you see what is the need, or like how do you do this slow and careful transformation, understanding all aspects of it, right? We'll go through that example very quickly. So any any mechanical system or any dynamic system is based on differential equations. We all know that. So what are these differential equations? They just tell you how quantities vary with respect to time, and then you solve them to get an initial and the final positions, or initial and final values, whatever it is, right? However, you have okay. Sorry about this. Yep. Yeah. Right. Okay. Yep. Sorry about that. Anyways, talking about dynamical systems, I mean mechanical. Talking about dynamics, you start off the dynamics with an initial manifold, right? Since what we observe in space, what we observe, what we can directly measure is changes of a particle in space, right? It is a particle is at point A, now it moves to point B. That is the most visible, discernible measurement that we physicists have, right? So the differences between the points in space, or in fact, to be more precise, the relativistic differences between position is something that is of that is considered fundamental, right? So the positions of a particle, or the position is taken as the base manifold, that is Q, right? You consider Q as the configuration or the base manifold of a system, and then how do you derive dynamics from it? You have to construct certain curves on this Q that the particle takes. Alright, so if you have a particle moving in a particular trajectory, the particle takes that curve, but not only does it take that curve, it has to take that curve in something, right? So there has to be some sort of a uniformness in the way the particle actually moves, right? That is why we define your tangent space, or your tangent vibration. So which is basically telling you, hey, I have this particle and it is moving uniformly with respect to time, or rather time is moving, time is spaced out at uniform intervals, and this particle is moving through time, right? So time there becomes a uniform parameter which generates this ability of some sort of commonality. I mean, it generates some commonality between different like trajectories of different particles, and that's why you have a local clock. So that is your tangent vibration, which is tau q, right? So it is basically construction of a linear space from your position manifold to your velocity manifold. I mean your tangent manifold, but it's rather like the coordinates of tq is nothing but q dot, which is dq by dt, where q is position and t is time. So t is time, or rather just a parameter which can be interpreted as time, right? So now you have your position which is given by q, you have q dot, and then you have p, the tangent, the cotangent manifold, your momenta, or rather it can be extrapolated to the Hamiltonian as well. So now what happens is, once you have these three things, then you have these double tangent spaces, where we will see how so we will see in a clearer example later, but basically what you need to remember is every time you go in from here, you go one level deeper, you have the ability to insert new parameters and play around with the differential equation much more, right? So now if you define p as the momenta, and then so there is some sort of an equivalence between these two. However, when you go to these the double tangent spaces, what happens is there are two things. One, there is an equivalence between positions and momenta, which is generated by this. So which is generated by the phase space. So position and momenta are considered to be parts of the phase space. So this kind of like so when you bring in the variational principles, especially for example p delta q minus p delta q dot minus q delta p dot, right? You see how if you look at the dimensions of p and q, they are actually very different, right? However, you can still construct some sort of linear spaces, phase spaces with both these variables treated on a similar fitting, right? What you need to remember is, when you transfer from each of these double tangent manifolds to when you transfer from one point to another on this chart. So this is a couple of notes about this diagram. It's a commutative diagram. That means that every time you travel across an arrow, there is a linear mapping, or there is some sort of a linear space that is given that describes this mapping. For example, if you go from Q to TQ, then your tau inverse Q will become d by dt. That is a linear mapping. That is a linear parameterization. There is a variation of a linear parameter, right, that you are generating, and that is how you transfer. That is how you go from one point of this graph to another point. So every thing here in all this, so you have this, and then you have the momenta by q, which is also another linear mapping, and so and at each point of your variables increase, your coordinates increase. So from here, if you go here, if you go to t star q, then you have both momenta and positions, right? So you have q dot, p dot, and you also have so you have all these dynamical variables here. So as in each particular tangent manifold, your ability to generate differential equations is limited. So if you look at TQ or T star Q, the ability to generate, you just have a limited number of variables at hand. However, if you go ahead to the second tangent spaces, then you get a lot more. You get a lot more interesting freedom to describe what it is, and how you do this is basically by giving certain constraints and imposing certain constraints on others, right? Now moving on, like we'll come back to this in a while. This will be the central idea behind this whole. This is the central idea or the central graph behind the diagram behind everything that mechanics deals with, right? So this is the structure of dynamical mechanics. However, so now we'll move on to talk a little bit about Morse families. So Morse families are nothing but in the simplest high school sense, whenever you're given a physical problem, you tell okay, so I have these many degrees of freedom or variables, and I have these many equations. So I can get one equation from the coefficient of friction, one equation from conservation of energy, momenta, etc., right? So all these equations are actually just differential equations that deal with variables, right? So now what you need to do is sometimes it can get a little more complicated from high school dynamics, right? So especially when things like complicated mixtures of rotation and translation come into picture, because of the number of mutual dependencies or on two or more orthogonal directions and all that, you can't just put a linear matrix, right? What you need is a Morse family of matrices. These are just equivalent to the number of equations that you have, right? The number of differential equations rather. So once you have Morse families, which is matrix, then you know if the system of equations is solvable if the number of equations equal the number of variables, right? That means you know that the system is solvable if the rank of the matrix is maximal. That means for every variation there is some sort of inequality. There is something on the other side of the equality. There is some sort of what is there on the other side of the equality. So why Morse families? Couple of quick reasons. One, as I said, the increased number of dimensions, and that it keeps you it gives a lot of flexibility in that way. The second is also because when you're talking about differential equations, you not only have first derivative, but you also have second derivatives, right? So these are two different kinds of differential equations which need to be categorized a little more carefully than just the normal way where you just solve 2 3 similar looking equations of similar kinds. But yeah, so this is what Morse family means. Now yeah, so look, so the Morse family looks something like this, right? So you have the second derivative of the Lagrangian with respect to constraints and the coordinates, and then you kind of solve them in order to if you have something on each something on the other side of the equality, then you do have a solvable system, or else you don't, right? Integrable system, or you don't, right? So given that, now what we need to understand is okay, so again the Hamiltonian picture and the Lagrangian picture, right? So as you saw in the brackets, I mean in the triangle diagram, there exists a linear mapping from the Lagrangian or dl to my dh, which is the Hamiltonian. However, one thing to note here is this has this has two, like you're taking it over two spaces, that is you have two products on the left hand side, and you have just one product on the right hand side, which means that there is a possibility that this, because these are like three variables, right? You have three variables, so just imagine there are three switches and there are two switches, and you're saying that the three switches are similar to the workings of two switches. Now there is a possibility that you can activate three switches in such a way that the two switches are not able to replicate. And then what we need to do is, this is a very simple analogy or a layperson's analogy, but here we go, right? So you have three and you have two, and in order to replicate the workings of these three switches perfectly, what you need to do is you need to add another switch, or you need to subtly insert a switch here, and that makes that gives an additional degree of freedom, or the ability to manipulate the working of these switches, right? So that in some cases, right? So you need to be able to do this as well. So given that, right, given that the fact, like it's a long and derived process as to how this equality is obtained in the first equality 401 is obtained in the first place, but yeah, so there exists a Legendre transform that takes your Lagrangian to the Hamiltonian at the end of the day. Right. Now, given this, right, you look at a couple of systems and then you say how I can transfer the Lagrangian from to the Hamiltonian, right? Now, but however, like I said, right, this is the, yeah. So before we move on to this particular example, right, there's something that I want to talk to you about is this concept of constraints or constraint dynamics. So now what constraint dynamics does is, given a physical system, you can deduct how some function remains invariant when you change it with respect to an arbitrary parameter, or if you introduce a new degree of freedom, you can say that, hey, you know what, this particular combination or this particular arrangement of variables is invariant under this new degree of freedom, right? So for example, in the simplest one, right, if rotation is invariant under translation along the axis of rotation, right? So the dynamics of rotations are invariant under this. So you can obtain a particular constraint from this whole setup, right? So how do you do that? Basic differential equation, you take this, you define a random function e, and then I mean it's not random, but it's rather you need to be careful about deciding what e is based on the dynamics of the system, and then you say that I vary it with respect to a new parameter or a new degree of freedom, and then I set it equal to 0 or equal to some constant, etc., whatever it is. So when you do that, the moment you do that, you obtain a constant, and it most happens that constraints are very similar to the idea of Lagrange multipliers, because in Lagrange multipliers what happens is when you take the Lagrangian and take the derivative of the Lagrangian with respect to something, most often it is the velocity. When you take the derivative of the Lagrangian with respect to that, then some part of the Lagrangian remains invariant, right? And you can ignore a particular part of the Lagrangian, right? So this is what your Lagrangian multiplier is, and you can see a slight correlation between the two concepts of constraints and Lagrange multipliers, right? So like I said, you can derive certain constraint equation from your whole setup of Morse families. So like your initial conditions or your initial assumptions are all your Morse families. The way you describe P, Q, everything, all the equations are your Morse families, and then they give you your like you can derive constraint from the Morse families based on, like, if you are a little careful about choosing what exactly remains invariant where. Okay, so now let us look at the example. Not to go too much into detail into the calculational part of it, but I would suggest everybody watching this to actually go through this particular paper in order to understand how and where the exact calculations come from. But what I want to do here again is just to capture the essence of this paper and talk about the basic ideas of problems that we have. Okay, so now so example 16, so you have a particular Lagrangian, and then okay, so you say that it is singular, right? So now you have a constraint and you have an energy function, which is basically you will see like how the constraint. So if you take the so your constraint here is basically your p square is equal to m square, that equation, right? So and then you're inserting some sort of dynamics for the charge. So this is your this is not exactly the electromagnetic Lagrangian, but it is a slight modification of that, right? So your charge E is and your field A. So basically when you're taking the this expression, it just tells you that hey, my mass is equal to m square is equal to p square, but not quite, right? I do also have to consider the action of the potential into the whole picture. So that is given by p minus ea. It's like it's like your position. It's like a momentum is being interfered with by the charge of the particle, and that also creates, like, combined with this whole general constraint that p square is equal to m square, you can have this sort of internal dynamics within the whole system, right? So that is what this equation basically means, right? And that is the idea of the constraint related to this particular Lagrangian. Now you have an energy function, and so basically you have an energy function, and you can derive from these constraints, you can derive what your changes in position and momenta look like, right? So you have something like this, right? And then you also notice that there is one constraint that you are entering, right? There is exactly one constraint that you have entered into the picture, right? I mean, one constraint variable that you have entered into the picture, that is this v here, right? So I mean, yeah, so I mean, this is the Lagrange multiplier, or yeah. So now when you look at so when you have the Lagrange multiplier here, so notice that it can take three values. One is the positive, negative, and 0, right? So corresponding to each of these multipliers, there is a different, I mean, there is a different dynamics. There is a different set of dynamics that is given by each value of the Lagrange multiplier. When you have it, when v is positive, it is one thing. When v is negative, it is one thing, and v is 0, it is another thing. When v is 0, both all dynamics is 0. Your q dot is 0 and your p dot is 0. So when it is negative, then you have p is given by mg. You have this the 420 relation, right? And so basically, right, what happens is there are two problems. One, your Lagrange is 0. I mean, your Lagrangian is 0, right? When your Lagrangian is 0, then it is problematic, because how do I take a 0 Lagrangian or a singular Lagrangian to the Hamiltonian? Like, how do I convert it? Right? That is the first problem that you actually have. The second problem is so when you solve for the system, when you do the Legendre transform for this particular equation here, for this particular Lagrangian here, okay, Lagrangian 413, right? So when you look at 413 and you take this Lagrangian and you do the Legendre mapping, then you find out that you get a single Hamiltonian, right? You get a single Hamiltonian and you say that, hey, my Hamiltonian dynamics is equal to my Lagrangian dynamics. However, this is not true, because you are losing out the essence of these zeros and the differences between the plus, minus, and zero Lagrange, zero values of the Lagrange multiplier. So, how do you correct it is the question, right? Is the big question that we are left with. So, in some cases, you're lucky enough, you can very easily obtain your the same richness of dynamics that is given by the Lagrangian in your Hamiltonian formalism as well. But in most cases, you cannot. You have to be a little more careful about the whole process in order to get a distinct dynamical structure in the Hamiltonian side of things as well. So now, given that we have understood somewhat the essence of the problem, let us briefly look at example 26. Now, integrability is basically when the system, so when the Morse family of equations is of maximal rank, right? That means the mass, that means the number of variables equal the number of equations in a broader sense, right? So now let us, in example 26, this is the interaction of two particles. So there are two particles and there is no external force, because when you talk about external forces in a relativistic sense, it leads to a lot of contrast and paradox and makes it unnecessarily muddy for this particular purpose of understanding what we're doing here. So there are no external forces, there are two particles, there is a gravitational interaction between them. There is it's all relativistic, right? So so you have the basic time-like movement of particles, that is they are physical particles. So these the set of relations for 77 just tell you that the particle is real and physical, right? And then you make some observations in order to make things simple, right? So now let's look at things, right? So when you make when you generate your dynamics, you get a generalized Dirac system that is given by these particular equations, p dot and like for 1 and 2, p and p dot for 1 and 2, right? And that you can derive from your Lagrangian by your basic Euler Lagrange equations or whatever. Yeah, so that is beside the point. However, your Hamiltonian, so you have your Hamiltonian, which is given by two Lagrange multipliers or two particular arbitrary variables that give you some sort of constraints, right? So now, so from here you derive a particular set of equations, right? So you derive q dot and p dot, right? I mean q dot and p dot, not q yet. Then from here you say that you introduce Hamiltonian vector fields, and then you say that everything, I'm making this whole thing linear, right? Whenever you introduce something called a Hamiltonian vector field, that means that, hey, I'm making this dynamics linear with respect to this particular combination of variables or this particular combination of vectors, right? So that is, then you, from there, once you insert Hamiltonian vector field, then you just have Poisson bracket relations, and you just have to solve for them, which is basically simplifying the whole problem of writing a complicated Lagrangian and then doing multiple getting the Euler Lagrange equations and all that, right? It's the whole it avoids the whole slippery trope. It just tells you that two operators commute or don't commute, and then you just have some sort of a Poisson bracket setup, and then you just solve for everything, right? So now what you do is you have a so your constraints are defined by the magnitude of p minus m bar 1, right? And this is p1 minus m bar 1 and p2 minus m bar 2. So what is this? This is basically the same thing of the previous constraint that we saw, right? P square is equal to n square. So in a kind of similar condensed manner, right? So this phi1 and phi2 are your constraint equation. So phi1 is equal to 0 and phi2 equal to 0 gives you your exact dynamics here. Okay, so now your constraint set, so you need to take this whole, like, you need to take the Hamiltonian and so its constraint should be equal. So if you define a constraint set, right, so this particular relation here means that your Hamiltonian in terms of two random parameters alpha 1 and alpha 2 with respect to phi 1 and phi 2 defined on the set C should be exact, right? So in order to get the in order for the constraint to be good enough, right? So we see that there are the constraints here are exactly not integrable because your alpha 1 and alpha 2 are really arbitrary, right? The only way these two can be integrable is if your V is constant, that is the potential that is interacting, that is the potential is constant, right? When the potential is constant, what happens, if you can simply notice it, like one equation is the flip side of the other equation. So you have this is equal to minus 1 and this is equal to plus 1. So then you just have to do a simple flip. Alpha is equal to minus alpha 2, alpha 1 is equal to minus alpha 2 becomes your like constant, and you solve, you get everything, right? So this is not integrable unless potential V is constant, right? So now however, so we move on from this example, and then we set these two constraints, and from this we obtain the equation from CC, and you do all this stuff. And so finally, so what you do is, if your potential is not constant, then you find out that you need to insert an additional constraint. How do you do this? How do you insert an additional constraint, right? So first thing, instead of like inserting an additional constraint, what we first do is we slightly change the variables of p and q, and therefore like we slightly rewrite the equations in a different way, and you try to get these constraints v1 plus v2 inside these equations, right? Understand, like earlier you had this alpha 1, wait, where is this? Yeah, you had alpha 2 and alpha 1 here, and instead of that we want to put them into this, right, in the middle of the equation. So the equation consists of both v1 and v2, right? So when you do that, and you try to say, hey, this might be solvable, right? So you try to like make it more solvable, but like it's clearly it's not. So once you do this, it looks like it is integrable, but you are actually losing out certain parts of the dynamics as well. So what you need to do is we need to really insert another constraints, right? So yeah, again you say, right, this is the whole thing, right? So you think that this is integrable, and this is solvable, but when you look at it a little more closely, you find that it is not really solvable, right? It is giving you the exact same thing as before, the exact same problems as before. Only thing is the way you're assuming v to be 0 is different, right? Because you're not including dv in the equation itself. So yeah, so now what happens is you need to insert an additional, I wouldn't say constraint, but I would say that you need to prolongate the set of differential equation into and bring in some other way to set this whole system of equation or like to be integrable, right? So when you when you see this, right, when you actually insert this, when you prolongate the equation, that is when you make it a mix of p dot and q instead of having your pure q's and p's, okay? So when you make a mix of p and q dots, right, when you take this particular mix of equation, when you jumble them up in the double tangent spaces, in this case it is t star q cross cube is two particles, right? So when you mix these up, you can get something that is integrable, right? So yeah, so and then you have like clear physical interpretation. So unless p1 plus p2 is 0, and so it's like you clearly have a restriction, and you know exactly where your system is solvable, right? And in the previous case, your potential was your barrier, or your potential was your so v is equal to excuse me. So v is the only condition that had to be 0 in order to give you an integrable system. But now you don't have that requirement anymore, but you do have like what it tells you to be physical, right? For the system to be physical, right? So we actually got a higher sense of understanding of the dynamics that is going on here when you do a slower and more careful Legendre transformation by kind of interchanging the values. Like you go to the double tangent space, and then you try to reformulate the set, this entire set of equation there by mixing p and q, right? So the other way that you can do is you can insert another, like I was saying, you can define another constraint, that is phi is equal to p1 plus pq into q2 minus q1. So that means either the overall positions are like overall momentas are positive, or like there is some the separation between them is real, then you just do have this particular constraint. So actually, so this, so you can set this whole thing to 0, and yeah, so what actually happens, because if you look at that particular Lagrangian, the Lagrangian here is not real, right? It means it is not the complete electromagnetic Lagrangian, so it has some big details missing out, and it cannot be physically possible. So what happens here is that your so you get to the conclusion that either your P1 plus P2 is 0, that is the net momenta is 0, or the net separation between them the particles is 0. That means that there is no real dynamics there, right? It's not a real yeah, it's not a I mean, it's not a real it doesn't give you physical dynamics, right? It is a Dirac system of equation. I mean, it is a system of equations, but it is not something that is physical. So this was the trick at the end of the day. So you take something that is not physical, and then you try to see how you can actually manipulate it and try to get an understanding of why it is not physical, and then you have this basic constraint that comes into picture. So your psi is equal to 0. So you have three constraints now. That is, phi1 is equal to 0, phi2 is equal to 0, and psi is equal to 0. We saw what phi1 and phi2 are already up here. Yeah, so you know what phi1 and phi2 here are already, and then you have psi also to be an additional constraint, and that gives you an integrable system. So in this sense, like, there are a lot of things, right? One is, how do you solve for Lagrangians that are not physical? How do you like look at everything that is not really what we observe? So how can you just write up a random set of equations and try to extract some sort of dynamics from them, right? And then what are these? How does the whole thing work? And the answer to all this is in understanding of how you prolong it from one set of differential equations to another set of equations. The simplest case of prolongation is, for example, if you talk about position, right? I mean, position to velocity, you have the tangent vibration from position to velocity. However, from velocity itself, so if you have q dot some function of some differential equation involving q dot, and then you have a differential equation involving q double dot, right? The set of differential equations, the set of solutions that are obtained when you solve q double dot are given by I mean, they restrict the values of q dot, the q dot equation. So what happens is, when you prolongate things, when you try to take the differential equations like into the second tangent vibrations, and you play along with it a little more, you actually end up getting some sort of new constraints and new restrictions to the whole system in order for the system to be solvable. Right? That does not mean that the solution is exact or you know exactly how it works, but that means that you have understood, or you have obtained a new constraint, or you have obtained a new set of restrictions that tell you like why the system is not real, or how where the system is real. So in this sense, your understanding has the understanding of the whole dynamics has actually increased quite a bit, right? From your normal rushing through from, hey, I have a Lagrangian, and then I just do the Legendre transform, and then I get a Hamiltonian. Okay, I make it like I derive the commutation relations and get the dynamics of equation. That is a kind of like a rushed up process through the whole thing, where you lose out most of the valuable information, most of the real understanding of the system. However, when you try to actually sit through this and notice all these things carefully, you end up getting you end up understanding the exact places where the whole setup doesn't work, or you end up understanding how to make it work if it is possible. So that's about it. So what we covered in brief: one, how does dynamics work? What is the whole structure of dynamics? Second, Legendre mapping exists, and therefore, like, you can go from Lagrangian to Hamiltonian pictures, right? And then third, we saw like we briefly saw what constraints are and Lagrange, right? How it is kind of closely interlinked to your Lagrange multiplier. So now then we saw how different Lagrangians lead to the same Hamiltonian, or Lagrangians are zero, and then we need to be careful about it. And then we looked at a particular example as to how we could actually extract a little more or a lot more information from this whole setup if we sit through the things a little carefully and a little more patiently and try to manipulate the system a little bit more, right? So with that, we're done for today. So again, all credits go to Tulcyzjew and Urbanski, and there's nothing new or original per se, but yes, there's only some interpretation and explanation that I gave. Anyways, see you guys. Thank you.